In this video, we're going to introduce the memory hierarchy of a GPU. So in the previous video, we shown this compute unit data structure. And in one part, we have the instruction fetcher needs to interact with the instruction memory. And on the other side, we also mentioned the scalar unit and the vector memory also need to interact with the memory system. Let's make this figure smaller. Let's connect the compute unit with the memory system. The instruction fetcher is connected to the L1I cache, which stands for L1 instruction cache. We also have a L1S scalar cache and the L1V vector cache. Then they have different organization. So for example, the L1I cache is 32 kilobyte and the read-only cache shared by 4 compute units. The L1S cache is 16 kilobytes. It's also read-only and also shared by 4 compute units. Because the compute units are very likely to execute the same program, and also some address and offset calculation may also be the same. Data loaded from the kernel arguments are likely to be the same. So if one compute unit loads the data, the other compute unit can directly use the data that is stored in the L1I or L1S cache. The L1V cache is for vectorized data. It's generally considered that the different threads may have different data, so it is not shared by compute unit. It is dedicated to each compute unit. It has 16 kilobytes in size. So different GPUs may have different configuration and may have different sizes. These sizes are for the R9 Nano GPU. So you can check the specification of the GPUs that you are using for the exact cache sizes. These caches are fully transparent to programmers, so if you write a heap program, you cannot really directly manipulate those caches. One important concept that is very special for GPU computing is called memory coalescing. It only happens in vector memory. So how memory coalescing works, you can consider that each wavefront may have 64 threads, and each thread may have a different address. And this address can point to the same location or point to very different locations. Let's make a very simple case. Let's assume all the threads are accessing the same part of data. We can either launch 64 memory transactions or combine them and only launch one memory transaction. So definitely the second option is much more efficient, it's energy efficient, and the performance is likely to be higher. In real kernels, it's not likely that the threads are accessing the same piece of data. They may access data next to each other. So some threads may accessing data in the same cache line. Since the memory transaction is always in a granularity of cache lines, we can combine the transactions that is accessing the same cache line into one cache line. When the data returns, then we can separate the data and write it into the registers belong to each thread. And the whole process is memory coalescing. Memory coalescing can significantly reduce the total number of memory transactions, save energy, and save bandwidth. So in this particular example, we see the 64 threads in one wavefront is accessing 3 cache lines. Now we can generate 3 transactions. But if we can remove the last 3 threads, we somehow can squeeze that 3 threads into the previous cache lines, we can actually reduce one memory transaction. If we have a scenario works like this, threads access some data, but it's just an offset that one piece of data needs to access one extra cache line. And this may have a significant performance implication that may reduce the overall performance because we're effectively changing 2 memory transactions into 3 memory transactions. Another implication is how we access data in 2-dimensional data. For example, if we have these row major matrices, then the data next to each other on the x-axis are data that is next to each other in the memory. So this data may have offset 00, 04, 08, and 0C. But on the y-axis, we may have this offset of 00, 1000, 200, 3000. If we want to access data horizontally, and these 64 pieces of data may coalesce into 4 memory transactions. But if we access the data vertically, then basically the GPU have no way to coalesce the data, and we have to generate 64 memory transactions. That means vertical access are very likely to be much slower than horizontal access. And we want to perform horizontal access rather than vertical access. Later on, in the next few units, we're going to see examples that how we can avoid vertical access and always access data in horizontally. And that is on vector memory. So memory coalescing doesn't exist in scalar memory, and memory coalescing doesn't exist in instruction memory. And also here I want to highlight there's an LDS unit. LDS unit is part of the memory hierarchy, but this memory hierarchy is within the compute unit. It's super fast. It's probably even faster than L1V cache. It's programmable, it's addressable, so users can determine which data goes to which address of LDS. So it's totally programmable and it's very fast. It's like a L1I cache, but you can program it. So we can utilize it to avoid a lot of memory access to the L1V cache, L2 cache, and DRAM, which is much slower than the LDS unit there. Later on, in a few units later, we'll focus on how to program your GPU kernels utilizing the LDS memory to make your program run faster. So far, we see the interface between the compute unit and the memory system. So how the memory system is organized, let's start with L1I cache. We said for 4 compute unit, there should be 4 L1V caches, and there should be 1 L1I caches and L1S caches. And in total, for R9 Nano GPU, there are 64 compute unit. So there are 16 groups of this compute unit and the L1 caches combination. The L1 caches are connected with L2 caches. The L2 caches provides the data for L1 caches. L2 caches doesn't have the differentiation between instruction, vector, or scalar caches. All the data are stored in the L2 caches directly. Now we typically say L2 caches are memory side caches because it's in a way each L2 cache is connected to a DRAM unit. It basically works in an interleaving way. So for example, this L2 cache and the DRAM combination may store data from 0K to 1K. And the second L2 and the DRAM unit may store data from 1K to 2K, those are addresses. Okay, and 2K to 3K and 7K to 8K. And we can go back to 9K to 10K, the first L1 and DRAM combination. We typically call this L2 and DRAM combination as a memory bank. And this memory bank is different from a DRAM bank. For R9 Nanos, it's likely to be interleaving at the cache line level or every 2 cache line level. So because of the interleaving granularity is low, we're very likely to access different part of data at the same time. So all these L2 caches and the DRAM can work together to provide the data to L1 caches. That can maximize the memory bandwidth between L1 caches and L2 caches. And also you need to always aware that these L1 caches are core side caches. That means each cache should cover the whole address space, although each L1 cache is smaller than L2 cache. And because L1 caches are core side caches and L2 caches are memory side caches, we need to use a big crossbar to connect all these L1 caches and L2 caches. So each L1 cache can access all the L2 caches. Each L2 cache can provide data to every L1 caches. A big problem that we want to discuss is cache coherency, how cache coherency is managed in a GPU, and what is the limitation for GPU cache coherency. Let's consider a few cases. So let's assume we have a piece of data in L2 cache, and this compute unit wants to read the data into L1V cache. This data is moved to L1V, and L1V provides this data to the compute unit. If the compute unit wants to write data to the L1V cache, because this L1V cache is a write-through cache. That means for every write transaction that goes through this L1V cache immediately forwards the write request to the L2 cache. So both the L1V cache and the L2 cache will have the most recent data. Now, the second compute unit wants to read the data, and data can move to this L1V cache, and the L1V cache forwards data to compute unit, and all three caches may have the most recent data. There's no problem in this case, and even for CPU, it works perfectly. But as we change the memory access pattern, things may become more complicated. Let's restart from the initial case. Let's suppose both the compute units need to read this piece of data. And this piece of data needs to be transferred to each L1V cache and each compute unit. So each L1V cache may have a copy of the same piece of data. Then, let's assume the first compute unit writes this piece of data. The L1V cache and L2 cache may have the update, but on the other side, the L1V cache doesn't really have the update. If this CU wants to read this data, there will be a problem. So coherency support in GPU is not perfect. In CPU, you don't see this problem. And in GPU, you do see this problem, and you have to use software to avoid this type of scenario. So as a summary, we have right through L1V caches that supports coherency at a certain degree, right? For the previous example, we can see coherency is guaranteed because every write goes to L2 caches. But the GPU cache coherency is not perfect. We don't have any coherency guaranteed there. And the memory consistency model is a weak consistency model. There's no memory access ordering guarantee. And finally, the implication tells us is that we should never read and write the same piece of data from the same threads. What we can do is we can either read one piece of data and write the same piece of data to the L12 cache. Okay, we can read the piece of data and write the same piece of data from the same thread directly to the L2 cache. That's okay. Or we can let each compute unit to write their own piece of data. And we should never write one piece of data from one compute unit and read that piece of data from another compute unit, and hopefully we can get the most recent data. We're not likely to be able to get the most recent data. And this only works for one kernel. If you say you write one piece of data in one kernel and read that piece of data in another kernel, we can flush L1V caches between kernel boundary. We don't have that coherency problem. If you want to write some data and read some data later in another thread, we have to stop the kernel and restart a new kernel. And finally, if you don't want to start another kernel, you always have atomic operations that you can use.